Hello, everyone. Welcome to the next part of this lecture. Again, we kind of started this lecture with an introduction to the Laplace transform, and our main objective was to really focus on this kind of switching events and made those models in the Laplace transform. And then the next lecture, we're going to kind of jump into the regular Laplace, finding Laplace transform on the operators and on the functions, and then start solving the circuits as well. So continuing, we kind of talked about in the previous half about the step function. Now we are going to focus on the impulse function and finish it up. So let's get started. Impulse function, again, if you remember, the impulse function is practically at zero. In zero duration, you get an infinite amplitude signature, right? This is usually called as an impulse function. So we are going to see what this impulse function is and what to do with that and how is this relevant in Laplace transform, right? Again, an impulse is a signal of infinite amplitude and zero duration. Okay, so circling back to what we learned in the previous half of this lecture about a step response, right? A step function. In a step function, we had a discontinuity, right? And the step function is not shifted in time, then the discontinuity is happening at t is equal to 0, right? So at t is equal to 0 in a step function, we have a step discontinuity occurs where the signal jumps from 0 to 1 value or 0 to a value k. In a unit step, it moves from 0 to 1. In a regular step function, the value k, which is the amplitude of the step function. So what we are practically interested in is, and this is what we are going to kind of develop an understanding on, that we are interested in finding the derivative in that transition where the step function moves from 0 to 1 or 0 to the value k, because the derivative of that transition or slope would practically be infinite, right? So we are interested in finding the derivative of a step function at its discontinuity at t is equal to 0, and we are going to realize that this is what exactly it means, that the impulse function is practically the derivative of the discontinuity at the step function of the step function. Okay, so again, step function, discontinuity at the step function at time t is equal to 0. We have to find the derivative of that, right? I'm going to show you in a second. And again, that small transition could potentially be modeled, that small transition that we were previously modeling from 0 negative to 0 positive, right? In this definition, we are modeling a 0 negative as minus epsilon, a very small time before 0, and plus epsilon, a very small time right after 0. And we are going to say that we have a very fast transition. Practically the same thing that we did for the step function previously. So we can model this thing over here. Minus epsilon, which was 0 negative, plus epsilon, which was 0 positive. We are calling this minus and plus epsilons here. And we are calling it that we have a very rapid linear transition in between minus epsilon to plus epsilon to reach a value 1, right? So this was the step that occurred at time t is equal to 0, or that abrupt change. And we are again interested in finding the derivative of that, right? So if I were to plot the derivative of that, before actually plotting, let's find out this equation, how this equation is coming. Again, this is a linear equation, so it must be coming from y equals mx plus c. So again, you need to find the slope and you need to find the c equals intercept. The intercept is 0.5 here, right? It is cutting the y-axis at plus 0.5, so c should be 0.5, and the slope should be delta y over delta x, right? So delta y is 1 to 0, 1, divided by delta x is minus epsilon to plus epsilon, right? So 2 epsilon. So your slope is 1 over 2 epsilon. So this is how the linear equation is coming. 1 over 2 epsilon times t, x is t, plus 0.5. Okay, now let's take a derivative of this function, because again, we are saying that the impulse is a derivative of the discontinuity of the step function, right? And this seems to be a step function, and the value is changing from 0 to 1 in a very short interval of time, minus epsilon to epsilon. So we are interested in finding the derivative of this function, okay? So the derivative of this function is shown over here. Again, before minus epsilon, the value was over here equals to 0. The derivative of the 0 is 0, right? So what is the derivative of this linear line? The derivative of this linear line, you can easily find the derivative with respect to t, which is going to come out to be 1 over 2 epsilon, right? So you get 1 over 2 epsilon here. And 1 over 2 epsilon derivative, this is this, right? So this is d by dt of f of t. Okay, so that, right, so the slope or the derivative is 1 over 2 epsilon. The slope and the derivative is the same. I hope you know that. Anyhow, so 1 over 2 epsilon is the derivative of the slope of this linear line. Once you do that, and this is only going to remain true in between minus epsilon to epsilon. After that, the derivative of this is going to come over, right? And the derivative of this thing, if you are going to take again a derivative of d over dt of e raised to power minus a t minus epsilon, it is going to come out to be again minus a, and then e raised to power same function minus a t minus epsilon, right? So this is over here. So again, this function represents the derivative of the above function, right? So, okay. So the thing to look for is a couple of interesting things, right? So the first thing is that let's find the area of the discontinuity. Again, in impulse is the derivative of the discontinuity of the step. So that is why I'm interested only in this kind of in this minus epsilon to epsilon, more importantly, which is a discontinuity of the step. Okay, so let's talk about this more. So first, let's find what is the total area under this discontinuity in this kind of a derivative of the discontinuity. So area, again, we are integrating minus epsilon to epsilon. So minus epsilon to epsilon over here. And the function over here is 1 over 2 epsilon. So 1 over 2 epsilon with respect to dt, right? So you can get 1 over 2 epsilon separately. And I can even solve it for you, right? Minus epsilon 1 over 2 epsilon dt is 1 over 2 epsilon separate. And then you get t minus epsilon, and then replace epsilon and epsilon over here. 1 over 2 epsilon minus epsilon, which will become 2 epsilon. And right, so the area is going to come out to be exactly equals to 1. Right, so which shows that over here that the area of this thing will come out to be 1 of this derivative of this discontinuity. Right, so interesting thing, the thing that I want to make it a point, and then I'm going to talk about this point again and again in the rest of this lecture, is that the area of this derivative of the function will remain the same, right, irrespective of your epsilon values. Now let's assume that you are going to reduce the epsilon value all the way to 0, right? So for example, now just assume that this epsilon minus epsilon is moving towards 0, plus epsilon is moving towards 0. You are reducing this rectangle. If you are reducing the rectangle and the area needs to be conserved, then the amplitude will increase. If you will again move it more closer to 0, this amplitude will increase even more. A time will come when epsilon will, on both ends, will squeeze all the way to 0. In order to preserve the area equals to 1, the amplitude will shoot up to infinite. And this is what we meant by an impulse function, right? That as we are squeezing these epsilon all the way to 0, as epsilons are approaching to 0, minus epsilon and epsilon on both ends, right? As it is approaching to 0, the area, in order to conserve the area, because area needs to be the same, in order to conserve the area, our amplitude is going to go all the way up. It's going to shoot all the way up. Right, okay? So practically we are saying that as epsilon approaches to 0, the function between plus minus epsilon approaches a unit impulse function denoted by delta t, right? Delta t. So, saying it again, we have a step function and we have a discontinuity of the step function. If we were to model that discontinuity and take a derivative of that, right? The derivative of that discontinuity is the unit impulse response. If of course if we have a unit step function. If the unit step function has a value k, then the area will remain k as well, as we are going to see shortly as well, right? So again, the point is the impulse function is the derivative of the discontinuity of the step function. I hope this will be clear. And in this, once we take a derivative, as we were kind of reducing this epsilon, squeezing this epsilon towards 0, in order to preserve the area, our amplitude continues to go increase all the way to infinity as epsilon will approach all the way to 0. Okay, moving on. Right, so derivative of f of t, which was a step function, at the origin, at the discontinuity, approaches a unit impulse function as epsilon approaches 0, right? So the derivative at 0 approaches unit impulse function as epsilon approaches 0. And this is what we also talked about, that in the previous slide, we had a unit step function. Not exactly unit step because we have an exponent going in, but our discontinuity has a unit response from 0 to 1. If that would be any other function k, then our total area under the curve would be k as well. And k is going to be referred to as a strength of the impulse function. So in short, the point that I'm trying to make is that we do not necessarily need to have a linear approximation of the transition or modeling the discontinuity. We can potentially model it in other ways as well. However, there are certain things that needs to be conserved for a function to be called as an impulse function, right? And I'm going to model it in a slightly different way as well. Right, again, impulse function can potentially be modeled with some other function with parameter epsilon, but that function needs to exhibit these characteristics. One, the amplitude of the function must approach infinity as the duration of the function approaches 0, right? And this must be true for the area to be conserved, no matter whatever the values of the epsilon are, right? As we have seen in the previous slide, let me show you, it's much more easier that way. Right, as I've shown you over here in this part of a picture, as our values of the epsilon are changing, right? For example, if I'm going to increase the value of epsilon, right, the height, this 1 over 2 epsilon will decrease, right? The height of this thing can potentially decrease if I'm going to increase the value of epsilon as well. And if I'm going to decrease the value of epsilon, the height of this rectangle will increase. And if the epsilon goes all the way to 0, the height goes all the way to infinite. Okay, where I was, slideshow current, right? So we can potentially model it in some other way, but the things that needs to be remain the same is that as your epsilon approaches 0, your amplitude should approach infinity. Okay, so let's see, are there any other functions that we can potentially model impulse functions? And the answer is yes. For example, here's another function. F of t equals k over 2 epsilon e raised to power minus mod of t epsilon. Again, this is defined as a mod of t because it can potentially be defined for both t less or greater than equals to 0, as we are going to do that shortly. Now let's see whether this satisfies this definition of an impulse function or not, right? So the first thing that we talked about, that the amplitude of the impulse function should become infinite at time t is equal to 0. So let's evaluate this function right? So I'm going to evaluate this function f of t at t is equal to 0. So practically you can actually see that, right? If you are going to put t is equal to 0, right, e raised to power minus 0 becomes 1, and the function comes out to be k over 2 epsilon, right? F of 0 is k over 2 epsilon. But this is the value of the function at t is equal to 0, but we are interested in the value of the function when epsilon approaches 0, right, over here. So this is f of 0. F of 0 comes out to be k over 2 epsilon. But I'm interested in its value when epsilon approaches all the way to 0. If the epsilon approaches all the way to 0, right, if epsilon is going to approach 0 over here, we know that the value of this function, or the amplitude of this function, is going to become infinite, right? K over 0 is infinite, right? So the peak height blows up as the pulse narrows. What I was talking about in the previous lecture, as you are going to squeeze a rectangle, for the area to be conserved, the height needs to increase. And if you are going to make the width 0, right, based on epsilon, the amplitude is going to become infinite. Okay, so the peak blows up as the pulse narrows. So that's one. The other important parameter over here is of the impulse function is that the impulse function only exists at t is equal to 0, right? Which means that it should be 0, right? The value of this function, f of t, this function, f of t, should be 0 everywhere other than t is equal to 0, right? other than t, why it says near t is equal to 0, because we are defining this kind of a duration of discontinuity here. Right, okay, so other than t is equal to 0, the value of the function will become practically become 0. Okay, so let's define this function, and we are going to say that the value, essentially what we are trying to do now is we are trying to prove that other than 0, for any value that is non-zero value, we are going to prove that f of t value comes out to be 0 to prove this point. Okay, so let's look at this exponent again, right? So we can potentially look at this exponent again, e raised to power minus mod of t over epsilon, right? Now, and the exponent of this exponent minus t over epsilon is written over here. So again, if I am, what is going to happen to this term if epsilon approaches to 0? If epsilon approaches to 0 over here, t over epsilon approaches to infinity, right? And then e raised to power minus infinity would approach to 0. And that is why you have this thing as, you have e raised to power minus t over epsilon 0, right? Again, for any value of t which is not equal to 0, if your epsilon will approach to 0, for any value t is not equals to 0, means that other than 0, everywhere else on the time axis, if your epsilon will approach to 0, this exponent term becomes 0. And if this exponent term becomes 0, then your f of t will become 0, right? So f of t will become 0 for every value of the t other than 0. So this also kinds of again prove that this function can potentially be used to model an impulse function. And again, we are saying that most of the pulse lives in this tiny duration which is proportional to epsilon, right? And if we are going to squeeze this epsilon to 0, the amplitude will become infinite. Okay, sounds good. So here is a representation, graphical representation of these functions, right? So for example, the function that I was showing you over here, right? Let me write it down over here. F of t is k over 2 epsilon e raised to power minus mod of t over epsilon, right? And just imagine that why this was mod of t, so you can define for t is less than 0, right? So this t is less than 0 and t is greater than 0, and you get to define it. And that is why you get these curves like this. But you still have a discontinuity. No, actually I take that back. There's no discontinuity here. So this is what's representing impulse function, or kind of the derivative of the derivative representation of some function, right? The discontinuity existed in the step function, and impulse function was a derivative of that, right? And one of the forms of the derivative that we have seen, sorry, let me clarify this thing. Going back, right? So one of the derivative form that we have seen was this. This is one of the model representation of a impulse function, which is a representation of a discontinuity. And here is another representation of the impulse function, and not a kind of a, yeah. If anything, this would be another way to model a derivative of a discontinuity in the step function. Okay. All right, so this is what it is. Now you can see that potentially, right, you can even pick different values of epsilon and draw these different curves. For example, now looking over here, one thing that you can see is, so for example, I could have not given you this thing and asked you this conceptual question, whether epsilon 1 would be greater than epsilon 2 or epsilon 2 would be greater than epsilon 1, right? And how would you know which curves belongs to epsilon 2 and which curves belongs to epsilon 1, right? Based on either one of these things. So for example, again, the concept is, as I'm squeezing the curves, right, my height increases. So if epsilon value, if epsilon is greater than 1, sorry, if epsilon 1 is greater than epsilon 2, this means that the height of my epsilon 1 curve should be smaller as compared to epsilon 2. So that is why your black is epsilon 1, right? So this is your epsilon 1 curve, and this blue one is your epsilon 2 curve, right? So if epsilon 1 on the time axis is higher, the height of this curve or height of this function would be shorter as well. Okay, so the third part that, again, in order for this to satisfy should be, again, we talked about that this function, that its amplitude goes to infinity as epsilon approaches 0 at t is equal to 0. And then we proved that its value will remain, its value only exists at t is equal to 0, and outside t is equal to 0, the value becomes exactly 0 for it to be an impulse function. The third thing that I need to prove is that its area under the curve will remains exactly equals to k for the entire curves, right? So here's the integral that comes out to be, and I can solve it in a second, right? So for example, I can define this integral from minus infinity to infinity, and f of epsilon of t dt, right? And I can divide that into into this portion separately, into this portion separately, minus infinity to 0. Just imagine this function, this, right? K over 2 epsilon e raised to r minus mod of epsilon t dt, and then this part. So let me solve this thing, right? So I am going to solve this thing into, first I'm going to solve this part, and then I'm going to solve this part, right? So minus infinity to 0. The first thing is that for t is less than 0, if t is going to be less than 0, mod of t will become equals to minus t, right? So your e raised to power minus mod of t over epsilon will become e raised to power minus t over epsilon, which becomes e equals t over epsilon. And similarly, for t is greater than 0, mod of t will become plus t, and e of minus mod of t over epsilon will become e over minus t over epsilon. Okay, so I kind of got this thing. Now let me solve for both of these things separately. Okay, so I'm going to solve first this. So integral of minus infinity of 0 k over 2 epsilon e raised to power minus mod of t over epsilon should be this. T over epsilon times dt should be minus infinity of 0 times k over 2 epsilon would be outside. And then I can, why don't I just, okay. So k over 2 epsilon will be out. And then e raised to power t over epsilon should be 1 over epsilon. Sorry, 1 divided by 1 over epsilon. And then e raised to power t over epsilon. Okay. And then again, and we need to solve this for minus infinity to 0. And epsilon will be cancelled with epsilon. So we will be left with k over 2 times e raised to power t over epsilon. So e raised to power 0 minus e raised to power minus infinity. E raised to power minus infinity is 0, and e raised to power 0 is 1. So you get k over 2, 1 minus 0, k over 2. Okay, great. Now let's solve the second integral, which is 0 to infinity, k over 2 epsilon e raised to power, and I'm going to use this, minus t over epsilon. So we get k over 2 epsilon, 1 over epsilon, and then e raised to power minus t over epsilon. And again, this should be actually this should be minus 1 over epsilon. And then this should be what? Infinity to 0. So epsilon will be cancelled out with epsilon, minus k over 2 times e raised to power minus infinity minus e raised to power minus 0 or 0. So you get minus k over 2 times 0 minus 1. You get another k over 2. So if you're going to do k over 2 plus k over 2, it's going to come out to be 1 when you're going to put down into this equation. So I just did this entire mathematical analysis, right? So once you're going to add both of the halves of k's, your answer is going to come out to be 1, which practically means that the total area under this entire curve will remain equals to k, and this will be conserved. And as epsilon will approach 0, right, your curve will get narrower and taller, but the area will remain k. So as epsilon approaches 0, f of t approaches to k times epsilon t. K times delta t, impulse function. So I hope this kind of clears it up. In the next lecture, we have like one more additional small concept to talk about, which is to take Laplace transform of f of t. of our impulse function, and then that would be the end of this lecture. All right, with that, thank you so much. Again, very briefly, in this lecture, I introduced you to a concept of an impulse function, which only exists at zero with an infinite amplitude. We said that we were interested in the switching event of a step function and a discontinuity of the step function. So if we were to take a derivative of that, right, it's which is derivative of the slope, right? If we take the derivative of the slope of the discontinuity, we would get an infinite answer, right? And that infinite represents an impulse. So the derivative of the discontinuity of the step function is an impulse function. So if we were to have a linear approximation of a step function discontinuity, we get one of the forms of the impulse function as this, which is kind of a rectangle. And we kind of looked at that, how this values approaches zero, as epsilon approaches zero, how the amplitudes approaches infinity. Then we said that we can potentially model it with any other function. By any other function, our relevant function, however, it needs to meet certain conditions. The first condition that we looked at is at time t is equal to zero, if epsilon approaches zero, the amplitude should become infinite, right? And then we looked at its value should remain zero everywhere else other than zero. And this is what we kind of proved that for all the non-zero values of t, our function comes out to be exactly zero. And third, we proved that the area under the curves will remain the same, will remain conserved. And this is how it's actually defined as an impulse function. The area will remain the curve, will be conserved and will remain k. Only then, as you shrink the epsilon, your amplitude of that function will increase, and you can model it as an impulse function. Otherwise, not. Okay, great. So with that, we're going to finish this lecture. Have a good rest of the day. Bye.